metric topology. Okay. Definition. A metric on a set X is a function. Say function D that maps X cross X to some R, having the properties D xy is going to be greater than or equal to 0 for all x, y, and x, where the equality holds if and only if x is y. And then secondly, we want dxy to be equal to dyx, all x, y, and x. And then thirdly, we want basically what's equivalent to the triangle inequality. Triangle inequality, which will give dxy plus dyz is going to be greater than or equal to dx z. And then that's all of x, y, z, and x. Okay, so then given a metric d on x, the number dxy is often called just the distance. Distance between x and y in the metric d. And then given a positive epsilon, we consider the set B for D the metric x epsilon to be the set of all points y, where dxy is less than epsilon. So of all points y whose distance from x is less than epsilon. And then it is he calls it an epsilon ball. I thought he was going to call it an open ball too. He called it an epsilon ball centered at x. And then the reason why he just calls it epsilon ball is because it's going to be related to being the basis for the metric topology, and since the basis is going to be their open sets, so to avoid redundancy of saying open sets as open epsilon. And then the definition here is that if D is a metric on the set X, then the collection of all epsilon balls be D x epsilon for x and x and positive epsilons. This is a basis for the metric topology. Metric topology induced by D. Induced by D. Okay. And then there's a little verification of this basis of the picture. is we have that x is in, so x is in the ball trivially. And then that's always going to be true regardless of what epsilon we have. And then if we choose to define our delta as epsilon minus dxy, which is going to be positive, then we have that the ball with y, and then now d is kind of like the radius of that ball, or delta. That will be a subset of the original ball with x and epsilon. Because if I have some point z in the ball with centered at y with delta, then that's going to give me that the distance between y and z is less than epsilon minus the distance between x and y, which will give that the distance between x and z is less than or equal to, if I then add this over, I just use the triangle inequality. So d and then xy plus dyz, which is less than epsilon. So what's going on here is if I have an epsilon ball centered at x, my x, and then that makes this measure right here the epsilon. And then if I have some other point y, so then if I've got another point y, then if I look at, so the distance, if I'm defining delta to be the epsilon distance and then the distance between x and y. So in dotted is the distance between x and y. And there's the difference, so this is delta. And then now I can just choose, if I were to choose, say, a z that is in this ball, then by the triangle inequality, here's xy, and then here's yz, which is going to be greater than equal to x to z. Okay. And so if we let P1 and B2 be basis elements, where y, and then we choose point y to be in their intersection. And then we can choose, basically what we showed here is that then I can have two deltas, so a delta 1 and a delta 2 that are positive, such that the b of y1 with delta 1 is a subset of the first basis element. And then I could also have a ball with y2 and delta 2, subset of the second basis element. And so then if I define my delta to just simply be the minimum, smaller one of the two, min of delta 1 and delta 2, then I can just use that one. So then the ball centered at the point y with the minimum of whatever it's going to be smaller between the two deltas, which is then a subset of this intersection. Okay. And then another note is that basically a way you can equivalently do a definition is to say that a set U is open in the metric topology induced by a metric D, induced by D, if and only if for all points in your open set there is going to exist a delta that's greater than 0, such that there is a ball y d that's a subset of your open set. Oh, yeah. Okay. Cool. So then the common examples at least that we Well, it's weird to say common examples because then it makes it feel like all of the math I've ever done in my entire life can be summarized in 2 examples in a textbook, and that doesn't feel so nice. But so if we have a set X, and then we can define a metric. So we can define dxy to be 1 whenever x and y are not the same. And then we can say that dxy will be 0 for when they are the same. And then this is the metric for the, this induces the discrete topology. Discrete topology comes from this metric. And because, for example, like if I took the ball for centered at x and then 1, that's just going to consist of x by top. And then when we have the standard metric, so this is all of real analysis goes off of the standard metric. Standard metric on the reals is dxy, and then just the difference between x and y. And then we already did triangle inequality and length last semester for this particular example. And then it also hurts a little bit when he says, it is obvious that, or easy to show. I'm thinking, we spent a lot of time on that. Okay. This induces order topology. So then the topology that this gives is the order topology on okay. There was a picture that went with this. So if I draw, actually, I'll just erase this space. Because it was nice to be able to pull on some analysis here. So like if I had, here's the reals. And then if I'm going to have a point X, and then the way you could interpret you choosing like the epsilons. So like if I had the ball, so to speak, is going to be X plus epsilon, X minus epsilon. And then in the, what we'll do is the basis elements are going to be, like if I choose some AB, so to go the other way, if I want AB to be some basis element, a ball X epsilon, we can always choose for this X, we can always choose X to be, if this is A, and if this is B, then it's going to be the midpoint. And then I can choose for epsilon to be halfway the distance. So I'll take B minus, or wait, hold on a second.
To be A plus B minus A over 2.
Wait, did I get it backwards? Oh, no, X's, we need to add these up. Yeah. This is the average, and then, yeah, this is the one where it's the difference. Epsilon is the distance. So B minus A over 2. There we go. Yeah. So then that's the conversion between the open sets and the epsilon balls. Right.
Yeah.
Okay. So then we can now define that if X is a topological space, then we say that X is metrizable. If there exists some metric D, metric on X that induces the topology. Of X. And a metric space metric space is a metrizable space X together with a specific metric D. Specific metric D that gives the topology of X. So from here, basically, he points out that there's a few things now, the difference between topological definitions, and then it's so abstract that lots of the things you do with it then become applications in, like, say, geometry or analysis. So for geometry, he basically just defined diameter in terms of the metrics. So let X be a metric space with metric D, then a subset of the metric space is said to be bounded if there is some M such that the metric to distance between 2 points A1 and A2 is less than or equal to M for all of the points A1 and A2 in the subset of the metric space. And if A is bounded and non-empty, then the diameter of the subset A is defined to be, and then we have the diameter of A will be the supremum of all of the distances A1 and A2 of distances in the subset A. So let's see, supremum. Yeah, so this would be the lowest upper bound of all of the distances in the subset. Okay. And then here, let X be a metric space with metric D. And then we can define D bar X cross S to R by dxy is equal to the minimum of either just dxy or 1. So basically, if we want a metric where that distance, if the distance is going to be greater than 1, just choose 1, and then everything under. So we're bounding it by 1 and below. Then D bar is a metric that induces the same topology as D.
Interesting.
And the metric D bar is the standard bounded metric. Right. Standard bounded metrics corresponding to D. So basically, it doesn't allow for these super big distances.
Okay, that one's interesting. Everything has been obvious so far, except that one. That one to me is not obvious. It is the same topology, but
Or it induces the same topology.
right.
So when we're talking about the reals, restricting basically to give a metric that is bounded at the top by 1 is still going to construct a bunch of open sets. Like essentially now, instead of just having, so that basis that you use to generate the order topology is just going to be now open sets where the distance between the points doesn't exceed 1.
Yeah, it's interesting. You can do that. Good.
Yeah.
So then you don't have to deal with infinity, even if it's
Exactly.
Okay.
Because that's how we handle. I think I did a proof of dealing with infinite case for it. And then we do take advantage of that restriction. Because if it gives the same topology, then if you can do something with the restriction, yeah, it's all good. Yeah, I had to stop about and think about that one. But I was like, wait, oh, yeah. All right. Try to fit these two. I'll fit these two definitions here. And then there's a big proof that we're going to do. Given some vector x, or I should call it a tuple, that's what we've been calling it. So x1 to xn in Rn, we define the norm. Favorite. The norm of x by the equation, and then we get norm of x is basically x1 squared plus all the way through xn squared, and then take the square root of that. And the Euclidean metric D on Rn is dxy is equal to then the norm of x minus y, which we can represent as all of the x1 minus y1 squared plus the dot plus through xn minus yn squared, and then the square root of that is the same. And then there's some interesting, he develops the definition of the square metric. Square metric given by rho is rho xy is, actually I'm gonna do this in a different line. So rho xy is going to take the maximum little distance in each of these. So x1 minus y1 through xn minus yn. So with relationship to the Euclidean metric, square metric is going to take a look at all the individual distances in R, essentially. Take the largest one of these and then treat that as the distance that's going to be used. So it's the largest represented piece of the Euclidean metric. Okay. And then lemma is that let D and D prime be two metrics on the set X, and that T and T prime be the topologies that they induce, respectively. then T prime is finer than T if and only if for all of the points in X and positive epsilons, there exists a positive delta such that the ball of under the metric B prime centered at X with delta is a subset of now on the ball with the metric D of X with epsilon. So essentially, if I was to draw circles again, it's going to be finer if I have for every single one of these balls, there's going to exist this metric that has a smaller ball contained inside as a subset. So we use this in the next. This is the lemma we're going to cite in the big proof. It's basically going to prove that the topologies on Rn induced by Euclidean metric D and the square metric are going to be the same product topology. So a little bit tougher than the other one, but it's useful. Useful in the sense that it justifies me doing the product topology last week. I like to feel like it wasn't a waste of time. All right. So theorem. This is I'm gonna have to just erase multiple. It's fine. Okay. So the topologies on Rn induced by the Euclidean metric D and the square metric rho are the same as the product topology on Rn. Product topology on R. And so the overall strategy is because the previous lemma is letting us know we could find when something's finer if we just find a ball basically that's a subset of the other ball. Then we'll do it both ways. Say this one's finer than that one, but that one's finer than that one. They're the same. Yeah. Because if we show that those are the same, then we only need to compare either the square, which the square metric is going to be easier to get to the basis of the product topology. So prove part 1 of 7. And we're going to start with letting a tuple x go x1 to xn, and then we need another one. So y is y1, yn. These are going to be in Rn. Then we have rho xy is not equal to, it's going to be less than or equal to the Euclidean metric between those, which is then less than or equal to the square root of n rho xy. And those is basically just algebraically manipulating the definition that we did on the previous board. And then so we'll use this inequality in 2 ways, the first part and the second part. So we have that since the square metric, so xy is less than or equal to d xy, that gives that the ball from d for x and epsilon is a subset of b under rho with x and epsilon. And that's going to be true for all of the tuples x and then positive epsilon. Well, I'll just say that epsilon because it's implied. And then that's because that the metric, Euclidean metric, dxy is less than epsilon, which gives that rho xy is also less than epsilon. And then if the second half of the inequality, so if I take d xy being less than or equal to the square root of n rho xy, that gives that the ball under row topology for x, and then we're multiplying this by square root of n, so then we'll just divide, so we got x and then epsilon over the square root of n is a subset of the ball for d and then x and epsilon. Again, for all x epsilon, and then this is giving that d and rho, and the metric topologies are the same by preceding lemma. And then now we want to show that the product topology is the same as the row topology. So we'll use the square metric. And that's part 2. Just gonna go, I'll try to fit the first part under here. So if we start, we need to let B and choose some basis element. So A1, B1 cross through AN, BN. And this is, I'll just say a basis element for the product topology. Okay. And then we'll also need a tuple, so let x be x1, xn in B.
Yeah.
Then for all of the I, we're going to index the epsilons here, epsilon sub I, such that we take xi minus epsilon I to xi plus epsilon I. That open set is a subset of the open set A sub I, B sub I. And so because of that, we just need to choose the smallest one. So if we just define epsilon to be the minimum of all of my epsilon 1 through epsilon n, for every single one of these open, then the ball for row x with epsilon is a subset of the basis element. And so that's going to tell us that the row topology is finer than the product topology. And so then when you're going to do the converse, we'll start with the product topology, and then we'll make it, basically choose it to be represented as finer than row topology.
This is a nice proof.
Yeah, it's pretty nice. It'll look funny at the end because the converse is going to be up here. But I'm dyslexic, so it'll work. Okay. So conversely, we're now gonna let the ball with row x and epsilon. This is now a basis element. Be a basis element for the row topology. Row topology. And then given a tuple in the row, in this basis zone. So given y and b row epsilon, we need to find a basis element. B for the product topology. Product topology such that if we have y in B, it needs to be a subset because we want it to be finer than the row topology. At least this is still citing the previous lemma. And so this is actually, I hate using this word, but it is trivial in this sense. Trivial, assuming you've understood every single definition somehow perfectly and understand everything. Because if we just take our ball, right, fall under the row topology of x and epsilon, then we've talked about what this is. It's just the x1 minus epsilon and x1 plus epsilon, all of these intervals that go across, so cross up to the nth one, so xn minus epsilon xn plus epsilon, these are all open, so this is already basically itself. So this is itself a basis element. Basis element for the product topology. Product topology. So the chain of conclusions is that the product topology is finer than the row topology. And we've already shown that the row topology is finer than the product topology. And so overall, so we can conclude that the product topology and row topology are the same. And then the first half was this saying then row topology is the D topology. And so all three are
That's nice. Probably important. I'm much happier with the metric spaces than I am with, must be my training, but I like metrics and norms. Maybe I'm an analysis, but yeah.
Because you did all that mathematical physics.
Yes.
They had you
Measuring.
I think I found that I can't tell if it's just because it's like seeing a familiar face, so you're naturally inclined to like be more friendly if you see a familiar face in a place that you're in a strange environment. So I'm not sure if it's the topology that I feel important in, or if my familiarity with some of the analysis stuff made me like it more. But who knows? I gotta give it some time. Okay. I don't know if we probably won't have time. Let's see. Okay. Actually, we might have time. Need the proof for that. Okay. Definition is given an index set J, and then X is the tuple X alpha J, and Y is the tuple Y alpha J, and these are going to be contained in Rj. We define a metric row bar on Rj y rho bar x y will be the supremum of all of the bounded dx alpha y alpha for the all in every single across basically the index set. And then where d bar is the standard bounded metric, is the standard bounded metric on R. Then we say that this rho bar is the uniform metric. Uniform metric on RJ. And the topology, it induces is the uniform topology. And since this is arbitrary to any j, then this does allow for infinite sizes. Okay, so then theorem is the uniform topology. Uniform topology on our j is finer than the product topology. Product topology and coarser than the box topology. Okay. And then when j is infinite, so these three topologies are all different. Wait, if j is infinite. Yeah. So that's the relationship between product topology or box topology. So the uniform is going to be in the middle of all of those. Let's see. Okay, I'll write down the theorem, and then if we have time to prove it, we'll prove it. The theorem be let d bar AB be the minimum of A minus B1. This is the standard bounded metric. The standard bounded metric on R. And so if the tuples x, y are in R omega, then we define d x, y to be the supremum of what the standard bounded metric gives between xi, yi over I. So whatever the lowest, whatever the greatest, yeah, or the lowest upper bound for all of the components. Then D is a metric that induces the product topology. Dun, dun, dun. On R. Okay, so this is treating the infinite case of where this will be different than the box topology. Yeah, we got time. Good, Jace?
Yeah.
Okay.
That's interesting. That they divided by I, which make it more.
Okay, so the the first two properties are just, you basically just plug it in. And then it's given by the definitions of the other one, so we'll just say. Those, well, at least they're not interesting, so properties 1 and 2. I won't say trivial again, I'll say are uninteresting. Uninteresting. 40. Okay. And so for 3, so basically showing triangle inequality, we're gonna note that for all of the i's, that we have this inequality where the standard bounded metric on xi zi over I is gonna be less than standard met xi yi plus yi to zi. Basically, we get this from this being a metric, so we already know that's a metric, and then dxy plus dy then, so that the supremum of dxi zi over I is going to be less than or equal to dxy plus dy. That.
Dr. Lang,
Hey.
Dr. Crawford.
Oh, hey, Doc.
There's somebody's voice from somewhere.
Yeah.
What show is the product?
You might have to continue next time, Scott.
Okay,
Well,
All right.
we'll leave it here and then finish.
Oh, it's yesterday in the.
No, you're good.
Yeah.